Thank you for coming. My name is Oleksandr Husev, and today we'll be somehow something like a lecture, but in my case, I always like a lecture, like a discussion. And so I see you have some laptops, lots of things to do, but still it was very convenient because usually I also ask you if they could be started. Okay. Also, if you have any questions at any moment, because it will be like discussion, because I try to force you to think about it for everything, right? But you also can ask any questions, right, that you have at any step that activities. Also, some advertising of PCB course who already visited that is good, but 10 years ago, actually, the CP design for me is something like part of art. And in my, let's say, school time, I was like a physician, first of all, I passed myself as a physician. And when you are thinking about PCB design, it's very close to physics. And you actually will talk today just about physics. And this is one of the good courses that I have been visiting in 2014, and I know that it's still active, and I do recommend it to have that option. But I just summarized what actually I visited there, or I saw there during that course. And the lecture will be divided into, let's say, three parts. First of all, we will talk about like definition of AMC itself, the physics of it, and actually somehow like some techniques in order to solve and to understand and solve most of the problems that you may have. Okay. So in terms of definition of AMC and what is important, right? So definition is on your screen. You can read. It's not a problem, but have to underline or like to define what is a force or PNC or what actual definition of electromagnetic compatibility. It means that how different devices can coexist when some can create emissions, some of them is coinciding with emissions. And also, you have to understand that devices that actually create emission, right? It's may suffer from the same emission. And we will discuss about this like during all this lecture. But why it's important? Okay, instead of introduction, we will discuss why it's important. So there is my opinion that it doesn't have any opportunity cost. What does it mean? Your bad design, in terms of production, costs the same or even more compared to good design. This is very important. And electromagnetic properties of light and such prevent improper function. So this feature is for different. From time to time, I like to say that it's not my design, but it was claimed that it can work for the question to you. Can it work for 2 kilowatt? Doesn't matter. It's something like mixed signal PCB design. You can recognize some common mode inductor input. I see some definitely people or like that person who tried to do that considers that you have something like you have different currents, right? Power current, digital current, probably, right? But can it work or not? In my opinion, it cannot work in the questions about this? Okay, or maybe argues, right? So also in terms of literature, in the end of lecture, you will see some references that I also strongly recommend to trust you. If you will search about this topic, you may find lots of books. This is just sunscreen. And sunscreen, it's quite difficult to read all of them. And also, what is also the problem? That in basic courses at university, it's not addressed at all. I don't know any good university that actually address in that level for like bachelor level of the students and the master students. Maybe you know better, but from my experience, the best what university can do usually is they teach you how to work now, but not about like power. I'm not interested in terms of how to say. I'm not the person. I'm not interested in how to do such some stuff in Outlook. I'm interested in why I have to do such stuff in Outlook. It's a completely different question. And why it's important if you're talking about like iterations, right? So think about how much time you spend usually in order to achieve proper performance of your PCB, despite that in simulation everything works perfectly. As it usually you design schematics, flag, build, fabrication, assembly, test. But you have problem. Need to do it again. And so I did it several times at the beginning because unfortunately I also in somehow I'm proud of my university, but at that time nobody teach me about this. So most of that knowledge I somehow derived by myself and digested by physics origin problems. But then also books, now information is available, YouTube and so on, but this iteration takes time. Fortunately, now I can say that most of our PCP works from the very first time, if we haven't done by very stupid technical mistakes, for example, like simply connected or connected to a pass or something. But in terms of like layouts, it should work perfectly from the very first time. But it takes lots of time if you didn't take into account, right? So, also why it's important because we approach an era of very high decision paper. And now our research topic now is megahertz frequency power converters working at kilowatts, 10 kilowatts. And in this case, if you're talking about megahertz, it's already radio frequency. And in this case, not saying that PCB is not important. PCB defines almost everything. Because simulation also forget about simulation. In simulation, it works perfectly, but this is a typical example. It's from our design, but it's typical PCB, which includes digital and analog circuits plus power electronics. This is so-called mixed signal PCB design. Mixed signal, what does it mean? That you have all type of signals or like different paths or currents that you have to address. And electromagnetic compatibility must be addressed, first of all, inside this PCB. Right? We are not talking about emissions that it creates for others. It's by default. But even to force this PCB work properly, because you have 600 volts or 350 volt DC link, plus you have 3.3 reference voltage for AD converter. And if you will say that it doesn't interact, that's not correct, right? So it was like about introduction, right? Why it's important. So this is like a summary. The goal of PMC is the correct operation in the same electromagnetic environment of different equipment which use electromagnetic phenomena and the avoidance of any interference effects. So, couple words about Altium. So, after these slides, I will not mention about Altium because anything that you need. Altium updates every year almost. It has new features, new libraries, and so on. And you just like need to Google, or you can ask Google, you can ask ChatGPT. Doesn't matter if you have some technical problem or like you don't know how to solve it. Please ask some Google and so on. You don't need technician or teachers for that. That's even I would admit the basic course at university because it's like now paradigm of education is going to change because if 20 years ago information itself was a problem, now information itself is not a problem. The problem is to digest this information in proper way and use that information properly, right? So, and now how to achieve EMC, right? So, emission issue. So first of all, you have to reduce electromagnetic generation that is created by your device. Right? It's one goal of any electromagnetic compatibility design because even I would underline two different terms like EMI, like electromagnetic interferences, and electromagnetic compatibility. Compatibility more complex. So, this is somehow an immunity issue, right? And second aspect that you have to think always immunity issues, the correct operation of electrical equipment in case of presence of unplanned electromagnetic disturbance. So if Your converter works in such environment when you may have other converters designed by not very well educated engineer. You still need to provide proper operation of your device, despite of that your device is working properly. Right? But the beauty of this physics is that usually, at least if you address at least one of them, usually you address both. What does it mean? That your device, which is properly designed in order to avoid like significant issues with electromagnetic emission, usually has very good also electromagnetic immunity. This is one of the main also conclusion that I will show you many times that it's like everything is interconnected. Okay. So now about standards, because formally I have to, because if you are talking about it, so we have to specify that we have like conducted emissions, right? That actually from 150 kilohertz to 30 megahertz, and it's definitely it's caused by somehow real mechanical connection of conducting elements. And radiated emission because electromagnetic energy propagated through space and here frequency range starts from 30 megahertz to 40 kilohertz. Well, to pass this certification, actually you have to think about, you have to like take this test and to see. And from my experience, when we were working in one startup company that was actually established here, all problems started when we faced the EMC standard. Because the converter they work in this like this very high efficiency, everything fine, then you need to reduce the cost, right? And then you need to pass certificate. This is standardization. And then you see that actually, I know that to pass this standardization, you need lots of extra elements or to redesign your PCB. And it becomes more expensive again. It's like a closed loop of iteration. And somehow it's not easy to address this particular case because art of design is always like matter of compromise between cost, efficiency, and to pass this step. So immunity issue, how to protect our circuits from external electromagnetic field, right? So, and there are several types of that. We will not discuss right now because after physical introduction or introduction about physics, we will come back to these issues because there will be several questions for you to discuss like the final part of the lecture. So, and where is it now? Let's actually switch to the second part. If you have any questions about the first part, you can ask, but it's both like introduction and definition, right? Not in new terms of energy. But now, physics origin about PCB, right? Power electronics, by default, it's conversion of energy, right? We convert one electric energy to another. And the question is, where is energy in PCB? Because, look, what does it mean? Power electronic and PCB represents power electronic. Energy comes in, comes out. Is it present in PCB or not? It's there. In the PCB present. In the PCB present. So, more than what represents energy in PCB? Huh? Losses, okay, yes, the field. Field, okay, it's better answer. So, because is it related to current? Yes, of course, right? Is it related to voltage? Yes, but no. Yeah. Because, first of all, do we need energy in PCB? Theoretically, no, but we actually, it's not avoidable because we still convert energy and energy will still be in PCB, right? But if you're talking about physics origin, you have to understand that energy is inside PCB and inside electric field, electric and magnetic fields. Current and voltage doesn't represent energy. you can't avoid current and voltage in PCB. So this is very big mistake that usually people don't think when they design PCB. And actually, it actually somehow even provides like biased somehow even by thinking that you concentrate about one stuff. It's not possible to avoid current and voltage in PCB by default, right? But now, why about the electric field and so on? Because energy of magnetic field. And now, actually, my favorite questions I ask them all the time when we start thinking about it. What is an inductor? You're all electrical engineers, and it's very simple question. Right? So, what is an inductance? At least two correct definitions. Okay, just imagine I'm your grandmother. Right, and you and your grandmother asked you electric engineers. Please explain me what is inductance. Change the flux of current. Sorry? Change the flux of current. Change the flux, okay, it works more or less better. But I don't understand change. What? Okay, there is some definition about this. At least I got your direction. And this is a physical value which shows how actually your passive elements resist to the current change. It's one of the definition. But I would like to talk about a classical definition of inductance, because you see, I saw also the figure, right? It relates to magnetic flux. So by definition, you have to say that this is a physical value, right? I can go here. This is a physical value which shows which magnetic flux is created by current in one amp. Right? So if you have conductor which has one amp current, right? And you have 1 million Henry, right? It shows you in reference of first what flux is created by this current. And there are several laws. We will talk about this because, as I said, we are talking about like physics origin of this problem. And you must know, and you must understand what does it mean inductor and how does it mean. Now also the second question that I also like to do. You have just imagined that you have some conductor, very simple one, AB. So it's just like a copper conductor. It has 1 meter length, right? And it has some L1 inductance. Does it have inductance by the way? It's just a wire. It has another. So any wire has inductance because across this there is a magnetic field that exists, right? But what I did the same wire and folded this wire with the same, it's still 1 meter, but inductance changed. Third case, I did something like this. I twisted at least 2 times. Else 3, right? So now question to you. You are all electric engineers, right? So say me, maybe like this? No. Oh, it's very good there, but okay. Your suggestion. L1, L2, which is larger, or maybe the same. So this one is larger, smaller, larger, or smaller. So this one, L1 is smaller. Who is that L1 is smaller? Uh, so like this, but I still don't feel confidence. But okay, this case, L2 is like. Maybe someone disagree.
It's I mean, now.
Okay, correct answer like this. Anat. Yeah. Because now, actually, why I ask about this? Because energy presented by magnetic field, not current. Current and inductance are only representative array. So we need to think about the magnetic field in this case. But before thinking, actually today I want to remind you several or like few basic physics equations or physics laws that you must remember, because we will come back to these laws several times, but we will consider traces and so on. So this is so-called Biot-Savart law for magnetic field. So each particle of your conductor creates magnetic field in all environment, but it's defined by this law. So as further you locate the point, as lower this magnetic field. And if you want to calculate magnetic field in this point created by total wire, you must integrate or like superposition, right? So if we will try to apply here, so, and if we have current in this direction, and obviously current comes back, right? So in this case, direction of electric magnetic field around is something like this, and magnetic field created by return current actually compensate each other. So definitely total magnetic flux much lower. By the way, here you see direction of the current. It's like in this case, it was in this case. You see the same direction. So, and here actually direction is opposite. So here vice versa. You have totally accumulated flux. That's why if here you have like subtraction, here you have like summing of contribution of different magnetic field, right? That's why here magnetic field will be the strongest. Here something like average. Here is the smallest. So this is a basic that you must remember when you think about direct and return passages. We will come back to this again. All right. Any questions about this? Huh? L1 is larger than L2 because there is no flux compensation. L3 is larger because here you will accumulate this in this total, because it's a little bit more complex question, but the strength of magnetic field this here will be much higher than strength of magnetic field in this case in any point. Here, all magnetic field will be concentrated here, or not all, but let's say something like much higher. Another Ampere law that we have to discuss. There is a simple, let's say, call like it's. I think it's even in school program. This is a derivation of Ampere law. This is somehow derivation of Ampere law for like a different derivative form, and it's used to obtain Maxwell equations also. But main meaning of this is that how you can calculate the stress of magnetic field. If you of magnetic field. If you enclose by some closed loop, and if you enclose magnetic field, right, you have your actually enclosure of this actually product of lens and magnetic field, right, integrated during this enclosure pass, you will have total current that is accumulated in this area. What does it mean in this case? If we have to define in this case, it's definitely that we will make a enclosure. Actually, if I will have like have a look from another side. This is current, right? This is just a current pass. So, and here you have definitely, here you have magnetic field like this. What does it mean here? That you can select something like, okay, you can select any explosion pass like this. And if it's total L, so L multiplied by B, but be aware that it's function of L, I mean, a function of certain geometric position. So it's not easy to calculate. But if we assume that here magnetic field is much lower than here, we can actually use only this pass, and it will be proportional to current included in this loop. But here you have, because you twist it several times, you have number of turns. And this is basic of, again, you calculate inductance. But inductance can be air-core, doesn't matter. Of course, if you use ferrite and you enclose your magnetic field inside ferrite, mostly, it's much easier to define. But what actually FEM analysis is usually analysis. If you use ANSYS to simulate, it calculates magnetic field in each point by this law of superposition. That's why, like, this basic equation is quite complex, let's say. But they say that you can calculate actually to any shape. You just need to define the magnetic field for each coordinate and then calculate this pass and define it. But actually, we are not here to practice in terms of like to find inductance and so on. But what we must understand how intuitively and like be aware whether you increase or decrease your inductance and whether you keep your magnetic field inside PCB. Okay. And here also, it's what actually this law shows. Because you may have, because you have direct, you will always have like a direct and return pass for current. But you also have to understand that it has also, it may have like this, right? Right, when you don't have a conductive pass during all pass. And here you have electric field, but this derivative form of law shows that you may have, this is a current density, but here is also derivative of electric field. And actually here it's very close. It's actually, this is part of Maxwell equation, which shows that any derivative of electric field creates magnetic field. And vice versa. This is a way how electromagnetic field propagates. Right? It's also available in the internet and so on. Another very important equation, or that you also must know, in my opinion, is by default. Because if you don't know this, you have to forget about like understanding. Because once again, the question is, you may know what to do, what pass you have to put in your PCB design, but you must understand why you are doing this. And second, very important part is so-called Gauss law. Gauss law is a little bit even more simple, but if you will talk about capacitance in the future, right, you have to use this also for definition. But here is electric field, which shows that electric field or total integration of electric field over the surface is defined by amount of charge located in this surface that you actually closed or enclosed. This is basic Gauss, so-called Gauss law. How it can be used? For example, very simple one. If you have capacitor that is charged, this is capacitor. Also very simplified representation, but here you have some plus charge. This is Q plus, here is Q minus, here you have minus, you have electric field inside, right? But we assume that electric field exists only here. And if you will take any closed surface like this, we will try to cover full surface. So in this case, Q is defined because, once again, you know that Q, or actually by capacitance, if you know the voltage, and you know capacitance, you know charge, right? So, and you have S, right? So this actually equation shows you that if you will multiply E by S, you you know this. But for what you have to use this, you need to use it for electric field definition. At least to understand where electric field will be present, where it will be compensated. And we will talk about this later. And actually, this is this example, definition of capacitor. Because once again, when I can ask you what is capacitance, you have to understand that this is like physical value, which shows what the voltage drop will be created, or if you have accumulated some certain amount of charge. So this is just a physical value which represents actually, finally, it represents electric field created by this charge. So, and the question is, where do fields travel in transmission line? So E and A fields travel entirely in the dielectric and are guided by copper features of your PCB, which act as a wave guide. So now we have to think about this, that your current and path, they don't have any energy. The energy is in the electric in your PCB. It's electric and magnetic field. And next, when you design your PCB, you must consider this, and actually only this. Your currents and voltage actually doesn't define your emissions. And the question is, reason of EMI in this case, magnetic and electric field spread out of your PCB. So you did it in that very bad way that you lose your energy, that actually you must convert your definition of power electronic is you want just to change one type of electric energy to another. But by some reason, you spreading this all over the world. Right? So conclusion is that some remarks about this. It's actually also Maxwell equation. Because if you spread magnetic field, especially if you are talking about gas frequency converter, or if you spread just you have derivative of electric field because it's not like the problem is that it's not like a constant electric. By Maxwell law, it creates propagation of electromagnetic waves because changing of electric field involves changing of magnetic and vice versa. By the way, the beauty sort of the parts-oriented, the beauty of Maxwell equation, that actually Maxwell was the first one who proved that sunlight is electromagnetic. Because when he derived the equations, he derived the constant, which was like speed of electromagnetic wave. And by that time, speed of light was experimentally measured, but it was still a debate what type you did. Another version. At that time, it wasn't proved that it has dispersion feature and so on. So that is electromagnetic wave at the time wasn't proved. But Maxwell just theoretically demonstrated that the electromagnetic field has speed of sunlight, which means that sunlight probably is electromagnetic. Okay? So, but this is a beauty of theoretical physics, which can predict actually the real physics. But why I mentioned this, just in order to keep this in there. So, but it shows how are we losing energy from PCB, right? So we just like to spread it out by that reason that we didn't make a proper PCB design and all our electric and magnetic field spreads out. So the question is how to reduce EMI? Keep energy inside PCB. So by this lecture is over. It was somehow the joke, right? We will discuss now, but this was a physical introduction. When you are making your layouts and so on, you have to think how to keep this energy inside PCB. This is example, like which shows you have like this is dielectric, this is pass for current, this is pass for current, this is pass for currents, but energy is inside electric field, first of all, and magnetic also. We will discuss how to keep this, is inside PCB, and it's not spread out, right? So this is a very simple conclusion. Keep energy field and means fields inside PCB. And now, step by step, we will discuss how to do that as the main tools, and you have to take into account when you put your layouts in PCB. Questions about this? Yeah.
By this statement, if energy and PCB, for radiated emissions or both radiated.
So look, we will show how it's mostly about radiated emission. But conductive emission, it means actually conductive emissions figures, it's a little bit different, but it's good question. And what does it mean conductive emission? Because we have energy in and energy out of DC by default. Because you have, I mean, for example, you have AC current for input and AC current out, right? Or like maybe constant current out. But conductive emission, it's a problem that is, we will discuss this later also. The problem of conductive emission that it's spread out by harmonics mostly, that is needed to convert your energy, but unfortunately comes out of your PCB. Ideal case, you need to have like a very constant current, like a straight line. But in fact, you have some frequency ripple, which actually comes out, and not only your direct conduction path, but also by parasitic capacitance and so on. And this is so-called conductive emission. In case of radiated emission, it's like this. But still, if you keep all your energy inside PCB, that is actually not needed to spread out. So this is like universal statement in any case. More questions? So, some intermediate conclusions. Actually, reduction of MI produced by your PCB is leading to enhancing immunity to external emissions and reduced interferences and increased immunity electromagnetic compatibility. So, but it's like more or less like obvious. AMC consideration for mixed signals and power electronic PCB. So, now several slides from actually that course I still use, but it's very nice. Because now we will come back to inductance in your PCB. So here it's nice illustration what I tried to do several minutes before, right? But every current flow origins in a magnetic field that acts as an inductance. It's clear, right? But what do you think? The length of the magnetic path around the conductor influences the amount of magnetic field. Does it make any difference compared to this? Imagine you have the same amount of copper, but they're just like smashed. Bigger. You know, you can say intuitively because this one you can't make in PCB, right? This one is better by default, right? But if you will apply USR law, actually, in that case, what I can do, I can compare something like this. If you have this shape and then you smash this shape, right, and current is equally distributed, just imagine that we have even constant current. Don't think about the skin effects a lot, right? But in this case, if you will apply USR law, you will see that inductance, total magnetic flux created by this somehow distributed current is lower because in these points, actually, they compensate each other. Here, they most likely relate. And here, this is a very famous equation that if you will put this X, and you have like B, strength of magnetic field, it's like this, where this is R values, right? So this is magnetic field actually enhance each other here, partially compensate. That's why like this always better in terms of inductance. So this is clear, right? So, but obviously I have hinting slides. Now, next case. Just like illustration. So Actually, I did never check this calculation. I truly trust, but even absolute values doesn't matter for me. It's important like value of comparison, right? And you see that here you have much lower, like the cable with a cross section of 1 square millimeter has an inductance of 100 nanoamp, right? But if you did it in the same way, but with certified micrometers, it reduced by 2 times with the same amount of copper. Okay. Now, inductance. Remember about direct and return current. So you have direct, you have return, and they compensated each other. This is that case when actually you keep energy inside PCB if you follow this rule. Because if you have direct and return current, like distributed in the PCB, they will not compensate flux of each other, right? But in this case, if they are really close, they will compensate, right? So this is clear. This is why actually I remind you about this BIOS over law physics and so on, right? Another example, you can put like this. You can put like this, right? So this is obviously different layers. And in this case, you have like the flat conductor with 0.4 distance, 30 millimeters width, and so on, show return inductance 2.1 nanoamp. So if you have return in direct path, and compared to previous case when you have just like a rounded cable without like this twisting to create return and direct path, compared to this, you reduce inductance 50 times, right? It works. Some obvious questions. Why actually it's bad and when you have to take into account this? Of course, you have to define when you are talking about your switching cells. Because look, what may happen in this case? Actually, I think most of you already tested something like this. Because switching cells exist in any power electronic converter. Right? And what happens if you have inductances here? How does it impact? In hard switching application, the DC-link inductance determines the voltage overshoot during switching. So this is somehow a good, not bad design, let's say, but still, this overshoot always almost present. And sometimes I even don't recommend to avoid it completely. Why? We will discuss a little bit later. But is it clear? Okay. So inductance, good example. Why good example? Because the obvious way. And in this case, what you have to do, actually, in this case, you have to minimize the switching cell. Always you have to understand that if you have very also some basic example, but quite useful, I think. Just imagine that by some limitations, sometimes like people ask, you have electrolytic capacitors that actually takes place something like this. And you have your half bridge transistor somewhere here. Right, and definitely you have plus minus, so you need to do something like this, right? Yes. But how you can minimize your switching cell if you don't have option to move this? Always you can put something very small here. And that's why it's always recommended to put distributed capacitor. Also, even in this case, if you count this pass like this, it will be always better than you put something like direct. It's a very simple explanation, but you keep return and direct current close together, which means it minimizes magnetic flux, it minimizes inductance. Clear. Okay? Despite that, you may think, oh, but it's shorter distance, lower inductance. No, inductance, it's by definition, it's how magnetic flux you create. And by this connection, you create lower magnetic flux. Clear? But there is a bad news. What about capacity? Yeah.
disputed. So is it like we should use some SMD components and capacitors to compensate and objects or they are
You always actually, I never seen any design when you use only electrolytic capacitor for switch and cell and you don't have any field or current capacitor. But usually it's only to, because if you can't move electric like electrolyte capacitor, which actually main source of energy, but you can always move small ceramic capacitor and put them as close to your switch and cell as possible. And in this case, you always minimize your inductance that is inside the switch. Okay. Also, favorite we'll discuss it later. You always may play with grounds in your PCB. I mean, the layouts in your PCB. Because your PCB creates capacitor by default. You just need to know. And we will talk now about capacitors. So, parasitic capacitor. Because we actually discussed what is capacitor. This is ability to create electric field if you have some charge difference, right? But if you did your inductance like we showed before, by smashed conductor, right? You by default you created parasitic capacitor, and that's sometimes not very good. So capacitive coupling mostly appears when interconnection lines overlap in multi-layer PCB, often ground and chases layers in power electronic devices. Now we will also pay significant attention to this because you may focus only on somehow like parasitic inductance and how to compensate inductance. But 2 years ago with one engineer from USA, we did a common paper about this that actually demonstrated that you can't focus on low inductance because if you create extra capacitor, it's even worse. So here we have so-called good and bad capacitors. Good capacitors. You have electrolytic capacitors, right? And look, orange and blue colors, it's different layers. So one is connected to plus, another connected to negative. And you see direct overlap. Definitely this is a capacitor. Is this capacitor good? It's DC-link capacitor, right? So this capacitor is good because also by definition, it will keep energy inside PCB between layers, right? No questions about it. So such configuration helps to avoid the parasitic inductance. Overlapping creates additional capacitance for DC-link. So first, and you see how, like, what is the tricky issue? From one side, you may concentrate only up to avoid parasitic inductance, but at the same time, you add parasitic capacitance, right? Is it good? But now think about another case. What happens if you create capacitor here? What is it good enough? No. Right? But can you do that? This extra capacitor, it's a huge problem, especially in high frequency devices. Because variation or change in voltage when actually it's supposed to be not conducting, or it was conducting, so it's zero, but then suddenly you switched off this transistor, which means that voltage rise up to some nominal DC-link voltage, but during this capacitive connection, you will have voltage across your gate signal. And you have here, for example, 350, but here you have GAN transistor, which has nominal 6 voltage, and at 9 voltage it will be killed. And you have some delta V, right, which may kill your transistor by just very bad design. So how it may happen? Actually, here, not all capacitors are good. And when you pay attention that you create some extra capacitors in your PCB, always pay attention, is it good capacitor or bad capacitor? This one, extremely not. So, Miller effect. This is demonstration of what I said, right? But what does it mean? That if you will calculate, this is GaN transistor PCB design, so this is voltage flow, so on, but it's from our personal experience. But when I just calculated all these parasitic capacitors, right, I understood that if we have 400 volts DC voltage, your spike across gate source will be 1.5 volts, which very close to the threshold of the opening transistor. It means that if you put this transistor in your ideal PCB, it will work. But if your PCB is not ideal, it cannot work. Or you need to introduce extra negative bias to both your transistors. But it's also the beauty of PCB design. If you have bad PCB design, you will pay to compensate that by extra elements, which actually adds extra cost to your PCB, extra space, and so on. But what can we do that? How can we do that? Because if you will talk about old IGBT transistors, and if you are talking about, look at the values, picofarads, right? Very small like values. But in case of GaN transistors, it's already a huge amount. They will be very sensitive. And what we did, what about PCB parasitic capacitance? This is just illustration, right? But this one, if you are thinking about drain source currents, right? Because you may do drain source that overlap each other, right? But in this case, overlapping also creates capacitance. You create drain source capacitance, which is not good. But also, which may be even worse, that 1 square centimeters give from 1 to 10 picofarad depending on the layers. If you will put this overlapping first and second layers that has minimal gap, it will be about 10 picofarads, when it's actually comparable to what you have in data sheets. Which means that if you will provide, okay, it's stupid mistake if I see that it's design, but if you add like drain and gate overlap, it immediately kills your operation. Just on this bit. Clear? About location of the layers, we will talk about this later. So, any questions about this? It's understandable? How much? So, capacitance exists everywhere. No. Because you have to understand that you have bad and good capacitance. Sometimes it's unavoidable, right? But parasitic capacitance in cable secure between the wire and the shell, or between the wire and the cable, roll respectively, and so on. So, this is something like basic, but also we have to take into account that we may have extremely bad capacitance, which creates like a direct conduction path for high frequency harmonics, right? It's now I just will talk about summary why it's bad, because it creates more space for common mode current easily, right? So when you design your transformer, you must always think about, let's say, about these problems that you may have distributed capacitor between primary and secondary winding, which actually may create lots of problems. But from my knowledge, in terms of transformer design, it's always a trade-off between leakage inductance and parasitic capacitor. And unfortunately, there is no way to achieve something like a zero. Both of them, you just need to set a priority. What is the priority in your case? What's friction frequency, and so on. So this is something basic, but if you need multi-layer winding, use a band winding, avoid that the first and the last winding are close together. So this is something like so well known. But about capacitance in clear. The main conclusion from previous few slides that not all capacitors are good. Even if you may think that you want to make, for example, if you have also, just one more point, if you have this outreach or switch and cell, you may think that I have also inductor here, right? And it's obvious that drain and source, it's direct and return current, right? So you may want to compensate this inductance, right? But in most cases, when you will compensate, you will add this. So what is better? It's if you have ZVS condition and you recharge your capacitors by this inductor, which is good. That's no problem. I do recommend to put this. But if you don't have, or you have hard switching condition, better to optimize that some overshoot may be present, but it's still like 10%, it's not a problem, but you will avoid extra capacitor and extra losses. Okay, so by default, that your inductance is bad, it's actually not always good at all. Especially in case of hard switching and, for example, non-semiconductors, I would think twice whether I will put extra capacitor. I mean, by just PCB layouts. Once again, if you've been working with IGBT transistors for hundreds amps, working with few kilohertz and so on, that issues mostly like somehow not so significant because you are talking about completely different frequencies. But in case of modern devices, like megahertz switching and so on, any your small parasitic capacitance is already sizable to what you may have in your PDF parameters. Right? And once again, this PCB design costs nothing for you in terms of extra costs for in terms of extra cost for your product, right? So about inductance and capacitors mostly over. Now somehow how to minimize or to use it wisely in your design. So first, avoid loops. So it's also the same principle. Return current, think about direct and return paths. This is better. This is not good. This is just better. This is like worse because you have higher loop. Next, a little bit more interesting, but still, you see this one is the best because if you have ground plane for your direct current, that's definitely, you will have the minimized inductance ever that you can do, right? Question to you, does it make difference? Maybe, maybe not. Because look, what's the idea? You have direct connection by relatively thin wire, right? But your return path in one case made like a ground plane, right? But in this case, but just imagine here you decided that, okay, I will save some copper. By the way, this is also a stupid mistake because copper in PCB by default is present. And by technology of production, you remove it. So you don't save anything. Okay. But you decided by some reason to save a copper and to put like here instead of this, right? Or you didn't have place for that. It's another story, right? But does it have impact in terms of like performance? There are two answers, yes or no. So first, yes. Maybe other as a shielding from other people.
Wider ground plane would be return current for other components as well.
Better.
Yes. So it may cause this interact with this watchdog and microplexing.
Direction is correct, but answer not followed. But look, almost the same. Return current will choose the way with smallest impedance. Why almost the same? If you consider constant current, you just imagine, right? This one is better because total impedance, like if you consider resistive impedance, it's better because resistance is smaller, right? But it's so negligible. But in terms of high frequency, current will select path with minimum inductance. And if you will increase switching frequency, you will see that current will select this path. It will not be used all this copper. If you will consider megahertz switching frequency, all current will be here. And actually here is, let's say, the distribution of current will be divided by direct current path, which is quite thin in our case. Clear? That's also important. Sometimes if you think about this, think about frequency, what you like thinking about, and therefore if it works or not, because you may shrink the size, you report something else, and so on. It's why like it's a matter of art. So in terms of loops, it's clear, right? Now about EMI filters. Somehow something first, we will discuss something very basic, but just to remind, let's say. So if you are discussing about EMI filter, differential mode noise, right? So differential, it's more or less clear, but you may have something like no source, it goes to load, which is not bad. So this is simple filter that is called like differential filter or X capacitor. Another localized high frequency supply filters provide optimum filtering and decoupling via short low inductance path. Also, if you use a plane, this is also not very good. This is much better because your current, if you have a plane, you will always find the shortest way in terms of minimizing inductance. Okay, this is something obvious, so I don't discuss it very like I don't want to stay there, but let's say the visualization is obvious that here you already defined this loop, which is not good. So always when you design PCBs, think about this direct and return path. And always remember about the basic physics law, which shows you whether you compensated your total magnetic and electric field or not. So EMI filters. Next, common mode noise. By definition, if you have capacitive connection, but you always have that, it's just a matter of how large is it. But you will have, and you have common mode voltage, you will have a path for reference ground surface. There is a way how to solve this. Is the suppresses noise. It's usually by common mode inductance. It's also something not new. It's just like comments, because little bit now I'm approaching to discuss a little bit more interesting things. But before, I just cover this basic one, right? So magnetic flux by differential mode currents cancel each other, and the impedance is zero, right? Next topic that you don't forget, it's X and Y's cups. Actually, in terms of technology, it's the same. It's just like definition of location of these cups. Usually, it's like when you have, in order to minimize your conduction emission, right, by high switching frequency harmonics, right, you need to use these X and Y cups. Here is location. Here is like a definition. If you have, and actually, what is the problem? That if you have differential noise, you have X capacitor, because, for example, this is actually equivalent circuit of your PCB, right? And it has differential and common mode noise, which is high frequency. For example, you inject AC current, but you have also high frequency current. I mean, you inject 50 Hertz AC current, but you still have these X and Y capacitors because you have this noise. But what does it mean? That if you put this Y and X cap, it means that you will keep this energy still circulating in PCB, not spreading out of your device. This is actually the main goal of these capacitors. Limitation. But why you must be careful? Because, for example, you have such system. You see, this is classical TNS grounding. Why it's needed for? This is also basic, but if you touch, right, you have this common ground current, right, which will go through our capacitor, but it doesn't matter, DC and AC, but it definitely will trigger your LCD device and system will be disconnected, right? But just imagine if you have extra capacitors that you put by yourself. Your current may not reach this. Your current partially will go here. That's why usually it's picofarads. if you think that, oh, but it's better if you put pico, nano, micro, and so on in your PCB, then your PCB definitely requires you to test this this test. You will test this test. Okay? So not everything is like if you don't understand the physics or actually the reason. And that's why actually sometimes PCB is not directly connected to ground, because in this case, you may create additional direct paths to avoid this protection. Uh, uh, This is just a feature, but it's important to notice. Okay. So why cups may destroy protection? Pay attention to P. So no questions about this. It's clear. Next, AD conversion design. Because we are talking about big signal PCB design, right? And I don't know any design that doesn't have this as well, because actually, if you want to make a cheap product, by default, you must consider this. Usually it should be like single PCB, because PCB itself not very costly, but assembling is more costly and so on. So it's usually one product must have like single PCB, which contains all parts, including control, measurement, and power part, right? So, and the problem is that you have, of course, low frequency signal, high frequency signal, right? But now we will talk about grounding and different grounds approach. Digital signal may cause significant problems on the board, right? But equivalent circuit. Let's think about this. This is one of the equivalent circuits that you may have. You have analog circuits, you have digital circuits, right? And you have, for example, common plane. About plane, if I will say to you that you must always separate, it's like analog and digital, it's not always true, and even sometimes in some lectures, what I think it's recommended to keep it this. But it just depends, because I understand why they may say this. They say that even if it's connected, it will still have a different path for digital and analog circuits. That's why, like physically, they can be really connected, but you just need to think always about direct and return current in terms of digital and analog circuits. And if here you have digital source, analog source, right? And your digital source has return pass like this. This is direct and then return pass. See? And your digital, if we have, what does it mean? Analog, you measure something like this, but in case of digital, you measure something, you have something like this. I mean, high switching frequency, right? But if you have here impedance, in case of common ground, this impedance will make distortion in your measurements. Is it clear why? Because they have a common path, right? In your digital path, which is actually not measurable, not easy to touch, but just actually in modern Altium design, you can estimate even impedance for some certain passes. It's actually possible, right? But I mean, impact of this you will feel only when you design everything and you have some, I don't know, unexpected oscillation in measurements. Have you ever faced that? I think yes, right? But then you need to cover the reason why you have that. But in simulation, everything is perfect. But in reality, you face such type of problems. So how to solve? It's schematic. It's just a schematic, but you definitely need to split analog and digital passes, right? And here is illustration. It's just illustration. Of course, it's not that you put some like separate wires. You know? It's a little bit, it's more difficult, right? But so that one is bad. This one is good. It's obvious, right? The first very important, the first obvious example here. If you have analog to digital converter, you quite often, not always, you have analog and digital ground. So split them. Right? Digital circuits and analog circuits split them physically. It's very convenient, right? But sometimes it's not possible. You may have circuits like this. You have analog to digital, you have SPI interface, right? Digital interface. You have analog interface, reference voltage, input voltage, and common ground. What they have to do is this. Right? But the one of the obvious solution, okay, you can even split these grounds here, or even you can do something like this. You can put a ferrite bit between them. You can split them. Why? Because ferrite bit is a huge impedance for digital signals, but almost zero impedance for analog signals. Right? This is one of the common approach that you have to do. Okay? So. Another, like mistakes in design. Resistive voltage drop causes incorrect measurements, loop antenna receives interference. So it's also, look, why it's bad. And now I would like to remind what I said that a unity issue and your interference issues are interconnected. Because if you have here relatively big loop, of course you have inductance, right? But also this is antenna for external electromagnetic field, right? Which means that you will measure actually high frequency noise of your transistors instead of measure the current of transistor. Clear? Questions? Because I'm approaching to the time when I will ask questions. Okay, so here is better design. First, you split power line, you split and you have differential one, but about differential we will talk later. Another also, one more feature. Total current in analog circuit, sum of useful and noise currents. Larger useful signal will cause less relative error. Also one approach, when you, for example, did a relatively bad PCB design, which has your amplifiers, which has your analog digital converter and so on. And unfortunately, it has noise. How to increase useful component in your signal? Because you know that, for example, you have operational amplifier. Which we notice is F2, R1 gain is defined by ratio. F2 to R1, right? So ratio is important, but what about total values? From one side, you want to increase them in order to reduce consumption. But if you have some problems with measurements, I always recommend to decrease this resistance in order to increase useful current. And it will increase your somehow noise immunity for measurements. It's not obvious what you do. Once again, you pay by extra losses by your bad design. But it may help if you don't want to redesign. So another approach, it's also something classical that most of you may know, that differential measurements. Differential measurements means that you actually split your signal or duplicate your signal to reverse one. And in this case, your total or your like impact of your noise can be subtracted, and you will measure only useful signal. In theory, it works. In practical, lots of you must be careful, because also when you are talking about, for example, you can try to use like this approach to measure microcontroller. But microcontroller, in most cases, has one or two AD units, but many AD channels, which means that they are not measured like simultaneously. And if you apply this differential approach, you must measure them simultaneously. For that, you must use only special differential channel. Otherwise, you will use measurements through multiplication. And in fact, why it's needed? In fact, you have some sinusoidal signals that you are measuring. Of course, this is reverse direct, and you assume that you have some noise which comes equally to both signals, and you measure them and subtract. But if in microcontroller, if you use not differential channels, but try to use this approach, one channel will be measured in this point, another channel will be used in this point. And you actually destroy all principle of differential approach because it uses a serious measurement, right, through the multiplexer. Okay. Questions? And just the practical remarks. So, positive, negative passes have the same distortions that can't be subtracted. Pay attention to the sampling time. Okay. So, key points in terms of AD conversion design. So, ADC choice, right? Analog versus digital ground, components location on the board, avoid loops. Right? Common mode choice and decoupled capacitors. Also, right, and power supply, avoid false convectors. I didn't mention directly, but here it's in most cases it's obvious, but for reference signal in your AD design, never use converters for reference voltage because it has very high noise. For that, usually it's recommended low noise LDOs, especially recommended for AD conversion. If you if you may somehow like you can think that you address all issues, but just didn't pay to only this aspect, it may destroy them. So next, more current, less noise. It's also, and different wires can improve noise protection. Differential wires. So, AD, some examples. Yeah, so it was just all PCB, but it was working quite well. So here was measured power electronic signals. This is something like analog circuits. You see, you have a ground plane for analog circuits, and you have a digital plane for digital circuits. See, they are split. It works perfectly. I didn't have any problems with that. This is one of the typical examples. They don't. Signals don't interact each other. Clear? So now about PCB layouts. Pay attention. Then when you order PCB, you have first, second, third, fourth. For example, if it's 4-layer. But what is a typical? Okay, so here. If you have 1.6 millimeter PCB design or PCB, right? You order. What is the thickness of this? Do you know? Have you ever paid attention to this?
Can you take it in the car?
Huh? 35. It's okay. This is a copper. 35 could be 70. 35 micrometer, 70 micrometer. But 1.6 millimeters, it means 1 micrometer, right? Agree. So you see, this is, yeah. What is the space? Where is the space? I'm interested in this distance and this.
Between layers.
Between layers.
0.2 millimeters.
Yes, 1.2 millimeter between these two layers, internal layers, right? And here, okay, it's around 0.2. You can calculate if you have total 1.6, right? But now, what does it mean in terms of, will you take this into account when you put your all type of signals in your PCB? And how? Because don't forget that when we are talking about overlapping, capacitor is proportional S divided by D. And if you create or you want to make overlapping between this and this layer, it's one distance. But if you create overlapping between this and this, it's totally another capacitance. That's why in previous slides, when I mentioned that parasitic capacitors went from 1 to 10 pico, actually I assume this. I mean, it depends on what layers I have this overlap. So ideal case, it's ideal case when you have, it's somehow structural representation, but it's not possible to split equally, like it's never possible, I have to say. But I mean, it's structural representation of ideal PCB design. You have forward power, return power. All electric and magnetic field inside this. Because this is high current, they define actually your main energy that is in PCB. And then you can use these layers for digital and analog. Digital, it could be analog ground, analog signal, digital, right? Yes. Of course, it's not always possible. And also one issue is that if you have something like 0.7 or like 70 micrometers, then 35, 70. 34, like you have 70, and this is also will be 70 because it's symmetrical. This is more expensive. And that's why, like you always, why I said this ideal case, but you have to pay for this case because this PCB will be more expensive. But why also? Because all the electric field is inside and it's not interferences with this side. Okay? Another case, let's say cheap one, but also not so bad. Forward power, return power, you may say that I need to use thick conduction layer to work with high power, right? So I don't have anything else, just like put this ground and keep this analog and digital as close as possible together, right? It's not, let's say, you see, not ideal, but acceptable. Yeah, but real PCB will be something like always trade-off. Some parts can be, but you always must think about direct and return paths. And then that's why, like, as I said, it's like art of design, because you always pay or you always like make a trade-off between cost, effectiveness, and so on, right? So questions about this? Is it clear for everyone? Now, why is I also important? Because if you are talking about loops, okay, we address returning direct current and so on, but then please pay attention to even these returning direct paths in terms of VS, right? Because here, if you did via here and via here, you still have a loop. Despite that it's loop very quite relatively small, right? But return current has a loop, and what I would do in this case, is it better? In this case, I will optimize the loop, right? It's even better. Will you pay for this? Oh, because you pay usually for number of years adds extra cost. Also, if you have some blended vias, it's terribly. It's like your PCB will go like 10 times more expensive. I don't recommend it to use it just for some specific case. But usually, if you have opportunity to put this via, and it doesn't matter in which place, just amount of that vias are important. But next illustration, source here. So you have this electric field and also magnetic field returning direct path. And if you have via for direct path, don't forget to put via for ground. You will minimize this loop. Okay? Especially in terms of digital signal, and we are talking about immunity of these signals. Okay? So, to the return current. Now, next topic, that you quite often, I convinced her, but about shielding. But my experience shows that not many of students usually understand this. Hope I didn't destroy this one. But Chu told me that I can draw, so I do this. Okay, so shielding. You see external electric field, you have just metal case. So please explain me, how does it work? What gonna be happen with electric field inside? Okay, I expected this answer, it is correct. Right, so it's called Faraday cage, but now we will play this a little bit. Because how can you use protection earth? 4, it means you have 4 layers. If you have not used copper, always remember your copper exists by default during PCB production. And if you remove from your PCB, you add extra cost. You don't make it cheaper, right? So if you pay attention, I will show also some examples. In our PCB design, we always have copper. If it's not used, we keep it like something like protection earth, so just not connected directly, but we can use by stitching BS and to make it like shield. And it's just immunity issue because it protects from external electric field. Or maybe, for example, electromagnetic wave that is created by your inductance that can be somehow near PCB, right? But all copper should be useful. And this is one of the examples, right? But is it always good? Now, look, what is the difference? This is a shield. This is a shield. Yeah, in one case grounded, in one case not grounded. Just imagine you have DC electric cable that has 800 volts, or doesn't matter what, actually, high voltage, for example.
There's a current flow maybe because of that connection between E and shading. They already.
Yeah, but look, look, you heard that you are shielding cable, you have that shielding on top of your useful wire. Sometimes you may hear a recommendation, is it grounded or not? Okay. I had experience about 7 years ago. I tested my converter, and then I did some extra shield, like because it was like a problem that my digital signal was disrupted. I made the shield for the digital signal. One person, like supposed to be engineer from the company, came to me and said, "Is it grounded or not?" Why? Because he heard that it should be grounded. I didn't argue with him and so on. I said, "No, it's not." But I will ask you, well, let's try to understand why it's important in each case. What should we remember? We have to remember Gauss' law.
So the charge will be stuck to the ground, second piece.
Yeah.
So it will be better shaded for external things.
Whereby
To avoid the interference with external.
So it's good for external or to our cable, for our circuit.
And it's good for external.
Okay. Any other opinion? And as for to answer this, you just need to know Gauss' law, and let's try to apply it. I have some doesn't matter wire or object that is positively charged. And we know from basic schools that electric field will be around this object, right? If it's variable electric field, so it will create variable electric field, variable magnetic field, and we have noise propagation, right? But then we did extra this like a shielding materials. This is actually metal around. And we talked before that it acts as a Faraday cage, because if you will draw here and you have some external electric field, in this case, you have, what will you have? You will have like a distribution of charge, which will create opposite electric field, which will compensate external. So, not grounded case protects our circuit from external electric field, right? Because pay attention, the total charge of this metal is still the same. It's neutral. Charges just distribute, right? Then I apply to this, because here what may happen, you have minus plus, you have minus plus. You will not have electric field inside, otherwise you would have a current, because it's conduction element. But if I will apply Gauss law in order to define electric field outside this, because total charge still defined by this, it's not changed. It means that the electric field is not eliminated, right? So it works to protect our devices that inside. This is Faraday cage. But if you ground it, in this case, you consider this like potential surface, which means that your plus signal will go down, and you will have only negative, which will compensate this circuit with this charge, which means that if in the first case we will have electric field something like this, in the second case we will have electric field something like this. So it doesn't protect device inside. That's why I calmly answered no. I actually care just about my device. I want to shield my device. Right? But if you ground it, then actually you protect other devices. So this is one important example where you must always think about when we talk about protection, but we have protection of the inside device. Yeah. What exactly is that protection? What, for example, you have inductor, even if it's with ferrite core, so on, it still produces electromagnetic interferences, especially it has a gap. And you have your 4-layer PCB, right? And this is like a device, but your inductor is located, it's schematical, of course, but it's located somewhere here, and it creates propagation of electromagnetic field around, right? But if you use your protection earth, it's called like a protection earth. It's not necessarily it must be connected. That's why I will underline that if it's connected, it will work in different way. But you can create Faraday cage to protect your digital and analog circuits inside the PCB. But pay attention to real grounding, because grounded will be another example when we will discuss that. So the difference, and actually what I want to show here, that you can use also by stitching, like you can use like if you have applied PE, it will be completely different. We protect our control system, but if grounding is reliable, it's also like very important. If you rely on grounding, right, pay attention that it's really grounded. Also, shielding in terms of this. We protect external from electric field caused by our power electronics. It's also, you see, completely like a difference in approach. Here, if you use grounded shielding, right? Statement, we protect external environment from electric field caused by our power electronics. So why ground and P not the same? In case of ground, I usually assume any plane that has a zero potential in relationship to signals that I have in PCB. In case of protection Earth, it's considered like ideal zero potential. Okay? This is like a little, it's completely different definition because your ground that you consider as a ground may not be ground itself. It could be even potential cannot be zero. Your static electricity and so usually if you need to connect by safety issues, no problem. You ground, if you have ground plane, which is used like a shield, it doesn't matter, connect it to through mega ohm resistance or capacitors. But also pay attention, this is CY capacitor. So value should be picofarad, not lasers. Okay. So another example. It's also one of my favorite example because my PhD students even face that problem. Difference between with and without P. What does it show? You have, look, capacitor here, right? Yes. Or you have just a plane, right? Where it's important. For example, guys, you have a transformer design, and this part is connected to first layer. Then you have second layer, then you have third layer, fourth layer. And you have second winding, which you connected to this fourth layer or third layer, doesn't it? Here is some other parts and so on. And here you can use as, and you see, you know that you need to avoid overlapping, otherwise you will create additional capacitors and so on, right? And you have plane here, and you have plane here. They are not overlapped, so capacitor is fine and so on. But then you added PE, protection earth, for example, some not used copper that you decided to use somehow, and you add it to PE. Is it good or not in this case? Just physics, nothing else. Impact, I am talking just about impact on this capacitor.
This substance is very increased because of that.
Because of P or just layer. First case, this is just a layer. Not connected to any ground protection. Oh, variance. Larger, smaller, zeros. No impact.
Like it's overall reducing the D, like because that substance is inversely proportional to distance between the layer. If we are keeping common layer, means we are decreasing the effective D, and if we are decreasing D, that means we are increasing the distance between the windings of water.
So, no, but look, okay. PE is available. PE plus total capacitor is higher or lower. PE is available. I mean connected. So what happens with this capacitor? Higher or lower? So, okay. Other option? who support this idea. Because the beauty of this topic is that actually you have to understand origin of this principles or like effects, because you may meet any other effect. It's just like an example for discussion. Because we also did once PCB, and it's supposed to be actually grounded. And in case of grounded, we measured it was like something like 6 picofarads. But then we removed ground in this case, and it was about 30 picofarads. And I asked guys, it's actually, for me, it was obvious. I didn't know. It was interesting how much it will impact, because theoretically, I know whether it's larger or smaller, or what type of impact it will have. But I definitely didn't know, like, couldn't predict in terms of absolute values, right? But it was interesting to measure. And the explanation is the following, that if you have so like floating metal, and if you have here plus, signal plus, here minus, right? It's like a capacitor, right? But what will happen with this layer? It will have minus, it will have plus, with total charge equal to 0, which means that you have equivalent circuits like this. And this is a series capacitor between this parasitic capacitor and this parasitic capacitor. But if you ground it, you made it like neutral, which means that your distribution charge will not work anymore in this way, which means that in this case, you will have like a parasitic capacitor between this and this, which actually much smaller because you don't have any overlap. Now that's why such small effect, but in one case, it may cause actually this value to this. You will we felt that because when you were working, we saw that oscillation related to this big capacitor between medians, and it had a crucial impact. As soon as we grounded, it disappeared. Okay. So I have something more or not, I don't know. So no grounded P makes everything worse. Okay, so that means that if you initially design for grounding, but you didn't do that, you may expect much worse operation. So we always watch out with this. Sometimes it's better not to rely on ground that is will be really connected to protection earth. It's better to avoid. Also, sometimes it's not good also from EMC issues as well. That's why by safety reason, your device must be connected to protection earth, but it's mostly it's like for the case, but not for your PCB itself. That's why your PCB not always must be connected to protection ground. Or if it can't be connected, in this case, think about what may happen if it doesn't, or like that connection disappears for some reason. Okay. So in terms of shielding, in terms of magnetic shielding, for that principle, quite the same, but you just need to use the permeable material. So I'm not going to discuss this like in details, but we will make some conclusions because it's lecture is coming to the end, but I'm open to answer all your questions, but some like intermediate conclusions. Use all copper on the boards, it's cheaper. So we just like example. You see definitely you may see some digital analog and high power passes, right? But we never remove copper just because it's cheaper, right? Keep magnetic and electric field inside the PCB. So this is eliminating loops. You have to increase immunity and decrease emissions also. Because if you have lower loop, definitely you will have lower noise immunity, higher noise immunity, and at the same time, definitely you will create like, or you will keep your field inside PCB. Yeah. And grounding and shielding demands careful attention and may require design iterations. And like careful attention, think about the basic physics. What you will cause if you connect or not connect. It's useful or not. Okay? Because if I would follow what that engineer told me, like have to ground, actually it would not help me what I wanted to do. I didn't start to explain to him because it may take some time and so on. So references. I put some, I will share this presentation. I put some also good YouTube videos published by one very experienced engineer. But he mostly published that in relation to mixed signal like digital and analog signals, like in most we consider for like data center design and so on, and more like for internet for like ESP for processing. But in any case, I think it's the same. Uh, Here you just need to add higher currents and higher voltage. So you need to keep also. I didn't talk about that clearance that you must take into account and so on. It's another issue that actually basically you know, right? But I just was talking about that EMC approaches how to minimize or like to improve your design and avoid some problems because it's always cause to problem and code iteration result. So that's all for now. Thank you for your attention. And if you have questions, yes.
And when it comes to parasitic interference and parasitic capacitance, so we have to do only one. So we should have select parasitic capacitance.
You want to say that we have to choose like trade-off between capacitor and inductance, right? Actually, there is like a Z. Also, this is L divided by C, right? So usually, if you have to decrease impedance, we are talking that you need to decrease inductance and increase capacitor. But what I said, in each particular case, like you have your ideal circuit in simulation. Just for example, you have PCM or another simulation tool when you put your ideal circuit. But then, when you obviously understand that by your design you add parasitic capacitor or inductance, right? Always think or ask yourself what will be worse. If, as I said, a very good example in case of if you have so-called switching cell with half bridge converter, and here you have inductance. If you have ZVS, I promise you, we can design PCB and you will have like this transient. We did it several times and you will put extra capacitor just by your PCB without any extra components, you know. But you have ZVS, it will discharge, it's not harmful. It will not add any losses. But if you have hard switching, I would keep little bit this instead of adding extra losses because this will add your somehow extra oscillation. But usually if it's like 350, you have 600 volts transistors, this definitely enough. So it's trade-off between like what you really need, just like analyze what is better in that case. Parasitic inductance or parasitic capacitor. That's why, and it depends. If you, for example, I have gate, train, so 1, 2, 3, TO 247, right? In one case, what I can do, definitely I know that I want to make them in one case, for example, I want to minimize inductance. And what I would do, I have here a thick pass, for example, and for drain, in this case, I will put, for example, even the same layer. I will put drain very close. Have I minimized inductance? Definitely yes. And in case of I have hard switching, it's definitely enough. But if I want to minimize even more and add extra capacitor, what I would do, I would use the second layer, strike after this, under this layer, and I would put a drain current like this, and even thicker. It adds, you see, it adds direct overlapping, it minimizes inductance and adds capacitance. But it adds capacitance, so your drain source capacitance is increased. But it's also like, if you will see, you will calculate this overlapping and you will see that you added something like 5 picofarads. And you will see that your silicon transistor actually doesn't suffer from that. It's like, come on, it doesn't important. It's not important. But if you will take a look on ground, it's a little bit different. In this case, it's important. So it's just matter of application.
What if we don't exactly overlap it?
Yeah.
We'll select the source, the bottom layer, and drain on the top layer, but kind of a loop.
It's possible.
So in that case, capacitance will increase,
If you have overlap in a drain source, yes, it's definitely will be increased.
and like no overlapping, but the drain.
But
of the
shifted.
top layer, yeah, shifted.
In this case, capacitor also will be available, but much lower. It's like 5 times for sure.
Like if I want to design a double layer PCB, so shall I put all the ground on the bottom layer and all the power line?
The bottom or ground, it doesn't important in terms of layers itself. What just I wanted to show by this picture, yeah, this is so-called ideal case, right? But what I wanted to show that first and second layer has very close distance, right? So this is very good if you locate power layers between like close to each other, right? That's why, but it can be like vice versa. It doesn't matter. First, second, it can be third and fourth, right? Also, you can have limitation in terms of thickness of this. If you have to design 35 micro here, internal 35, in this case, you can use second option also. You know, it's definitely not ideal because you will have electric and magnetic field passes through your digital and analog circuits, right? But it also, look, in some part of the PCB, you can use like first approach, like this. In some part, you can use another approach. It just depends. It's art of design because sometimes you have limitation in terms of size. If you have the limitation in terms of size, we can make, I don't know, a driver circuit, for example, in vertical infrastructure. It's just like a basic learning somehow like this piece of art and limitation that you have. You know, and it's not possible to say that in this particular case, do just like this. You know, it's just a basic, like I can say what is better, what is worse, but what is your final choice? It just depends on some certain like requirements that you have. Okay. Or if you have so compact PCB design that everything must be very close to each other. Good questions?
I have a question about gears. Like, like we are using a gear per se, we don't touch it also.
You will use a gear and you have what?
So you said that if we are using a gear like signal,
Yes.
we must have a gear. So
Not must have, it's not that word, but it's like if you still care about your like immunity or like your possible destruction, you like it's better to use gear for ground near your digital signal. Because just always think about the return and direct path, and you will see that it must be as close as possible to each other.
where should we post it?
Yes, if you have here for direct current, like you have seal casting, put also, and you like switch between legs, put also here for ground is a point close to them.
And usually we use multiple gears per phase, and previously, but here also has interface value for the product part.
Like in the past, you know, you have a pass, you have like any conductor has inductor. Yes, it says by default, but inductor, by default, inductor, it's like what should have been created. You know, what I try to do to show at the beginning that inductance doesn't depend just on the amount of copper. It depends on like mutual location or returning direct path. If the currents compensate each other and the magnetic flux is compensated, in the same BS will have much lower inductance. So that was like a message of for that initial introduction from physics. Because even though what is bad if you don't understand the physics, you try to learn this like, I don't know, some law without understanding, or some violence without understanding. But it's quite flexible. If you don't understand origin of the approach, you can make a huge mistakes. You know, like that protection rules should be connected, should not be, and so on. You will face lots of trouble. And it will be like random design. No, but it's a good question. Yes, and also it's important. You will not feel definitely immediate with the people, you know, because it may not have direct or visible. But it definitely doesn't have also extra cost. That's why it doesn't have opportunity cost when you have a good PCB design.
About the how many years have you used like in 2 years, 2 years to get exactly minimum base? Most like they increase it also. No, it's just easy. The commercial things are
We just did with we had some crazy idea with remember with Matushkin to design some PCB integrated magnetic inductor, and we wanted to use also like years between layers. But instead of $100, which we expect for like even from China, we got it in for 1,000. And they said, look, this time not. Because technology is completely different. Because when you do years between layers, you know, it's so like your our cost of PCB production is calculated. First, you remove copper, then you make drills, and then you put together, right? With this first two, then third, fourth. But if you have also both blended, so like this is yes, but technology is possible even to do like this, but it's much costly. Because in one case you just drill whole PCB, which is easier. In this case, it's not easy. Even here at this stage, if you do drills here, it's also like more expensive.
But I read in some material from our team that for signal in inner layers, you should use like these blind vias, even though it's more expensive.
Should no, you know, it should. It's not that work. If you are ready to pay for that, fine. So, in art of PCB is to solve tasks that you have, like proper operation. There's probably some EMC requirements, but for lower cost. So then, it is like unavoidable. I never met such cases, honestly, in my experience, that it's just like unavoidable, and I must pay for this. In this case, okay. But in most cases, I never met the case. I guess it's unavoidable. Increase your PCB size, for example, if you don't have space. It will be much cheaper compared to make that very big.
will be distributed capacitance properly. How things are doing the policy, then we should take care of that capacity should be distributed.
It means that if you have switch and cell, and for example, you have some long wires. It doesn't matter it's in PCB or not in PCB, and then you have this so-called switch and cell, which is connected to capacitor that is located here. But you have these like inductance. It creates magnetic field. But if you will put some capacitors that is very close to this switch and cell, it's actually from switching point of view, you don't have this conflict switching between inductors. And this capacitor creates you and like creates your this mitigation of this. It's like cut off this inductance impact. And it could be achieved by several ways. Of course, you have to put extra capacitors. Then, if you're talking about layers, definitely make overlapping of this layer. It just will create extra capacitor. It's good. Just use wisely what that copper that you have.
was thinking when you said, distribute capacitors, I was thinking what could be the value and how one, if someone can.
Well, it defines very like, say simple, but not very simple way. But if you know somehow you can estimate these parasitic inductance, right? During the switches, you need to know how much energy you can accumulate here. So, like your energy will be redirected to this valve. And if this energy or this capacitance for energy is larger than this, it means that you will have enough capacitance in order to avoid any spark. Okay. All right, if no questions, hope it was useful. Thank you for attention.